So we're going to work on enamine hydrolysis. Basically, we're going to start with an enamine, and we're going to talk about how to take it off, right? Get rid of the nitrogen. Right? So one of the intermediates we found was this. So enamines are nice because enamines are nucleophiles. So this right now is in the best case scenario. So what will happen here is that the H will fall off, electrons will go up, and this will make an enamine. And we made H plus. So now we have an enamine. Enamines are nicer than enols, right, which is the oxygen version, right, the OH in a pi bond, which of course is different than an enolate. But an enol is nice because this is nitrogen now instead of an oxygen. And what do we know about nitrogen? Nitrogen is more willing to donate its lone pairs. So it's going to be a better nucleophile. Remember, the nucleophile is always at this alpha carbon. Right? So let's say I've made the enamine, I've put this on. This is like the last step. I'm going to put in an electrophile. So I'm going to put in this electrophile, this 3-carbon piece with bromine. Messing it all up. So I'll put in this 3-carbon piece with bromine. We just said enamines are nucleophiles, so they're nucleophiles at the alpha carbon. So let's have the lone pair on the nitrogen come down. As it does that, the alpha carbon attacks and kicks out the bromine, right, just like an SN2 reaction. So what do we have now? Now we formed a new, the electrons came down from the nitrogen, so we formed a new pi bond. So now the nitrogen has 4 bonds, so it has a plus charge. On the alpha carbon, we've added a new bond, 3 new carbon piece. Looks good. We'll get there in a second. It's just one step at a time. So now we've done that. What else do we have left to do? Balance our charge, Br minus. So now at this point, right, we can return this back, right? Is this going to want to stay like this? No, it's going to probably turn back into an enamine. Right? So if we have an H here, right, it's going to turn back into an enamine. Now it'll stay like this, right, until we add either another electrophile or, using the last step here, if we want to get rid, now we're going to actually do the hydrolysis. So now we're actually doing this hydrolysis. We have an enamine, we've added something, right? Enamine was a nucleophile, we added an electrophile, we've made a new carbon-carbon bond. This is great. But now I don't want the enamine anymore. Now I want to get back to the ketone, or the aldehyde in these cases. So what are we going to add in? We're going to add in H plus and water, H3O plus. H plus is a great electrophile, probably one of the best. Lone pairs on the nitrogen come down just like before. The alpha carbon is still the nucleophile. Right? This alpha carbon is still the nucleophile. That's where the new H bond is going to end up. CH bond is going to end up. So now we have the nitrogen again with the plus charge. But now water's floating around. And this looks like a pretty good electrophilic carbon to me. Let's have water attack that and form a tetrahedral intermediate. I'm going to shrink some stuff up here a little bit. Now we'll go down. Let's form a tetrahedral intermediate. So now we have the nitrogen. We just added the water. The plus charge on the oxygen. Right, so we just added the water. We have a tetrahedral intermediate, so we ask ourselves, what's the best leaving group? The best leaving group here is water, but we just added the water. So we should do a proton transfer. Plus, we should be thinking, right, the whole goal of this is to get rid of the amine, right? So we should be trying to make the amine part a better leaving group. So we do a proton transfer. Now, tetrahedral intermediate, the best leaving group is the amine. And the H plus is a catalyst. So we'll have the OH bond break. Those 2 electrons go there. Those 2 electrons go to the amine. What do we end up with? Now we have the ketone back with the new carbon-carbon bond we formed. We have the amine back that we originally started with, and we also have H plus. Remember, this H is this H. As those 2 electrons leave, right, that's this H, the new pi bond. All right, we're going to try to see, I have a question. I'm going to shrink this up a little bit. So questioning maybe this intermediate and maybe try to make it react a different way. So I'm going to redraw that intermediate. And so the question is, if there's H plus around in water, why not have the nitrogen lone pairs grab it? Right? Okay, so let's do that. Let's see what we get. Plus charge there. Pi bond. Now what do you want to do?
Push the electrons from the pi bond to the carbon and then keep both the Na.
Push the electrons from the pi bond to, so let me number the carbons.
You're gonna have
1,
a lone
2,
pair to-
3, 4, 5, 6. Where do you want me to push electrons towards?
to the carbon 2, and then that
So-
bond breaks over.
So break this bond, have electrons go to carbon 2.
Yeah.
So it'll be evident why we won't want to do this in a second, I think. Right, so we always want to minimize charge whenever possible. So if I put electrons on carbon 2, that has a negative charge.
No,
Where's the plus charge going to be at now? Who lost electrons?
No, okay, but then take both the nitrogen.
How would I kick it off?
Flow of electrons.
I can't push electrons, right? I would make a pi, the nitrogen already has 4 bonds. It can't have any more bonds. I can't push electrons towards it. My
thing is it has a positive charge.
has positive charge, so the bond I need to break is this one.
Yeah.
Pushing electrons towards it, so,
So you're breaking that and then you're gonna have a lone pair of the carbon.
but now it's a carbene. So there's that carbon, right? Carbon 2 has what bonded to it right now? Carbon 1, there's nitrogen, and carbon 3 twice. So if I break this bond, this carbon only has 2 bonds now, and a lone pair.
So that can happen, but it's just not likely.
No, yeah, yeah. So don't get yourself in a big mess with these, right? Always remember, it's nucleophilic. Enamines, enolates, enols are nucleophilic at the alpha carbon, right? The alpha carbon, that's the part that's nucleophilic. That's the part that's nucleophilic. But it's good. You gotta go through this and convince yourself, right? If you don't write it out and convince yourself, right, you can't purge that idea out of your head. You gotta write it out. Otherwise, because as soon as you get to a test, you're going to try to do what you initially wanted to do. So write it all out. Prove it to yourself it's not right. So this is number 12 in chapter 18. Now they're saying they have 2 of these aldehydes. Now be careful with aldehydes, because how many alpha CHs can aldehydes have? Like how many types? Only 1. Alpha CHs. How many alpha CHs can aldehydes have? This is not an alpha CH. Not an alpha CH. Not an alpha CH. Not an alpha CH. Not an alpha CH.
I thought you said number.
Yep. Two numbers here. 1 type. That's right. All right. But it says we have 2 of these, and they're saying we're going to treat this in OH minus and some ethanol. We're going to heat this bad boy up. So when you see that OH minus, you see heat. What's going to happen is something called an aldol condensation. So aldehydes, al-dol, usually alcohol, aldol. 2 aldehydes come together, form a ketone and an alcohol. That's an aldol reaction. An aldol condensation, though, is when 2 aldehydes come together and they condense something. What do we usually condense? Water, right? So we're going to lose water here. So we're going to make a pi bond. We're going to do elimination 2 at the end. So there's 2 of these, so I'm just going to draw another one. So one of these is going to be the nucleophile, and one of them is going to be the electrophile. They're going to react with each other. That's why we have two. So the first one, strong base, kicks up. We make the enolate. So one aldehyde now effectively becomes a nucleophile. The other aldehyde is going to be the electrophile. And where are aldehydes electrophilic at? Where are they delta plus? C of the carbonyl, the carbon of the carbonyl. All right, so let's number our carbons. Let's see. We'll call that guy alpha because that's the nucleophile, the alpha carbon. We'll say this is 1 and 2. So we need to make a bond between the alpha and 1, right? So the electrons come down. Pi bond attacks. Electrons go up. 3 arrows. Check that down a little bit. All right. So what do we get? So let's make sure we have the bonds right. I think we have a new pi bond, right? We still have the aldehyde back, right? If this is our alpha carbon, that's now bonded to carbon 1, right? So this would be 1, this would be 1, this would be 2. What else is bonded to 2? 2 had the, oh, nope, don't lose a carbon.
Oh, there are two of them. I missed that.
2 was bonded to the phenyl ring. And what else is bonded to 1? What am I missing? How about the O? O minus, right? And that H is still there as well, right? You got to number your carbons with these. Got to do it. You're gonna lose carbons otherwise. I almost did it. I almost did it, and I did number my carbons. So now at this point, initially, when we had the OH minus attack, we also made, right, when the OH minus took that H, we made water. So right now we have a tetrahedral intermediate, and we have a tetrahedral intermediate. What do you ask yourselves? Do I have any good leaving groups? Do you have any good leaving groups here? No. Right? So that means you're going to probably protonate. Well, the only thing left in there is that, so we protonate that. And this heat is kind of a giveaway. When you see heat, right, it's a little more reactive conditions, right? Things are kind of cooking. We made OH minus again. Well, now, are there any alpha CHs left? How many alpha CHs did we start with? Oops, I lost something, didn't I? This was still there. Does that make you feel better? Right, so we replaced one alpha CH with this whole group right here, right? Right, we deprotonated. Now we have this whole group. But is there another alpha CH left? There is. So guess what? OH minus can take that alpha CH, and you could do it just like an E2 style, kick out the OH and regenerate OH minus. Now, why would it want to do this, do you guys think? Why would I want to do that elimination in this case? Especially in this case. Why would I want to? Let's take a look at this product. Why would I want to have another pi bond? Because I do. Oops. This is my original alpha carbon. That's 1, and that's 2. Why would I want to have a pi bond all of a sudden? Resonance. It's conjugated now, right? It's more conjugation. That's always good, right? More conjugation is good, right? Don't forget, this is a benzene ring, so it's now conjugated up here too and there. Yay. Right? So OH minus in this case is a catalyst, actually. Right? And that extra bit of heat helps you do this elimination, right? Because is OH minus a very good leaving group? No, not really. But this extra bit of heat and the fact that you make something that's conjugated makes it possible. So this is called the Aldol Aldehydes, usually alcohol, hence the OL, but an Aldol condensation. because you're making a pi bond. Right? You're making that pi bond. And overall, what else did you make here? Right? Water. Right? OH minus and this H, that formed water. Condensation reaction. Condensed water. All right, so let's talk about Grignards. And let's talk about hydrides. And what they work with and what they won't work with. Right? So Grignards are species that have a carbon with a negative charge. Right? They have an ionic bond to magnesium. Right? So be careful. Right? One thing I've been surprised about is people don't understand the difference between an ionic bond and a covalent bond. Right? So sometimes we draw it. Right? We'll draw a Grignard looking like this. Right? We'll draw it looking like a covalent bond, but we don't mean that. Right? You know something about electronegativity and know that carbon is much more electronegative than a magnesium. Right? Magnesium on the far left side of the periodic table. These will still have H's as well. Right? So Grignards react like a C minus. So is carbon happy with a negative charge? No, it's super reactive. So the trick here is you got to be careful if you have heteroatoms with bonds to hydrogen. Right? Because first and foremost, C minus is going to act like a base. So it's going to take an OH from a carboxylic acid for sure, right? It's an acid. From an alcohol, right? Grignard is a super strong reactive base. So it doesn't, even an NH, which isn't a very good acid at all, is going to react with a Grignard. Right? Because carbon, who would you rather have a negative charge? Carbon or nitrogen? Nitrogen. Right? So Grignards are going to not be compatible with carboxylic acids, sulfur, SHs, NHs, or OHs. So if you see those, the Grignard is going to react with those first, and not the carbon or the carbonyl, which we usually want it to. Right? So you got to be careful with Grignards. Hydrides are the same way, but it depends on where your hydride source is. Right? So lithium, remember aluminum hydride is much more reactive. So aluminum hydride, right, will actually deprotonate alcohols. Right? But the H minus source from sodium borohydride will not. Right? It's not that reactive, so it's not going to, usually won't deprotonate an alcohol. Right? But they'll both, of course, deprotonate, guess what? An acid. Right? H minus is going to take that acid, you're going to make H2 gas. So something to be aware of and think about. Right? If there's a carboxylic acid around, remember I've told you this before. First and foremost, a carboxylic acid is an acid, hence the name. Right? So it reacts different than an ester. Even though they have the same amount of reactivity, right? The same place on Mount Carbonyl, they definitely react differently, right? Because acids, carboxylic acids, have a second component that's also reactive, where an ester probably doesn't. So kind of like a basic discussion on pKa and how this relates to the alpha carbon CH. So I would break it up into two parts. Single carbonyls, monocarbonyls, and dicarbonyls. So let's look at the monocarbonyls first. So something like an aldehyde, a ketone, an ester, and an amide. And we're looking at the alpha CH bond. Now the acidity or the reactivity of all of these bonds, all of these CH bonds, is directly related to how delta plus the carbon of the carbonyl is. Aldehydes, carbon of the carbonyl, is more delta plus than a ketone, right? Because of hyperconjugation. A ketone is carbon of the carbonyl is more reactive than an ester because an ester can do resonance. An ester, alpha carbon of the carbonyl, is more reactive than an amide because a nitrogen does resonance better than an oxygen. So it's the exact same logic as we use to define why this carbon, this carbon is more reactive than this carbon, and this carbon of the carbonyl is more reactive than that carbon of the carbonyl. Same exact logic, just applied to the alpha CH now. So this would be, oops, so this is the most acidic within this group to least acidic. Now don't get thrown off, because what happens if I do this? What about this carbonyl? What kind of carbonyl is that again? So which one's the most acidic of all these? Now that I have 5 there, which one of these do you think is the most acidic? Probably the carboxylic acid, right? Trick. Right. You'll see that in the old tests. I threw that curveball in like 3 or 4 times. Right. So this is actually right amongst right. This is the most acidic, right? It's no way. It's a carboxylic acid. Right. So be careful with the carboxylic acid trick, because of course the carboxylic acid is more acidic. It's an acid. Right. So that's the monocarbonyls. But now what if we do dicarbonyls? That changes things up a little bit, because now it's basically factoring in 2 carbonyls. And there, of course, are pKa numbers to go with this. But now we have a dicarbonyl. Which hydrogen are we most focused on? We're most focused on the alpha CH that's between the 2 carbonyls. All right? Most focused on this alpha CH. Right? Because that one can do more resonance. Right? It can do resonance either way. But now we just look at it and say, okay, this has a ketone and an aldehyde. This has 2 ketones. Well, aldehyde is more reactive than a ketone. This would be more acidic, right? Because the 2 ketones kind of cancel each other out. Right? That's a wash. But an aldehyde's this carbon's more delta plus than the carbon of a ketone, so that's going to make this bond that much more reactive, make this a better acid. 2 ketones versus a ketone and an ester. Well, ketones are a wash. Ketone versus ester. Ketone's more reactive, right? More delta plus. That makes this bond that much more reactive. This is going to be the better acid. Ketone and ester versus 2 esters. Well, esters are a wash. Ketone versus an ester, right? This is going to be a better acid because, right, the ketone's more delta plus there. So this CH bond is going to become more reactive because it's going to feel, right, there's going to be a more polar bond, right, because a ketone is a more delta plus carbon of the carbonyl than an ester does. Right? So that's kind of the logic. So it's the same, this is the most acidic, this would be the least acidic. Now these are more acidic, right? 2 carbonyls is always better than 1. So these are more acidic than these, as a general rule. I won't throw anything too tricky at you, right? But as a general rule, 2 carbonyls is better than 1.